Hello and welcome to the seventh session of the course. The course name is Advanced Thermodynamics and Kinetics. I am Umar Rashid and I am working as a PhD student in Indian Institute of Science, Bangalore. So I held a session for 2 hours every week on Friday from 6 to 8. In this session I help you to solve the questions that have been given in the assignments or some other questions, and while solving those questions I am briefly revising the concepts of this course that will be used to solve the questions that we are trying to solve. Okay, so previously we in the previous lectures that are available on the YouTube, we have talked about different concepts and solved many questions regarding the kinetics, regarding the electrochemistry, thermodynamics, gas fluidics, and also the kinetic theory of the gases. So today we have another session. So today we'll be mostly talking about the spectra. Okay, whether be it a molecular spectra or or an atomic spectra. Okay, so okay, so we'll briefly discuss about different spectra and how the structure of the energy levels inside an atom or inside a molecule affects the spectra, and what are the information that we can get from the spectra, and what are the different types of the molecular spectra. Okay, so without wasting any more time, let us start today. Okay, so okay, so the first concept regarding the spectra is that you might have seen that different kinds of the spectra, whether be it an NMR, atomic spectra, UV visible spectra, or an IR spectra, that we see different lines. The lines can be really sharp lines, or they can be very broad peaks. Okay, so all these lines or peaks, they tell us about the energy levels in that system. Okay, so in order to get a spectra, it has two types. Okay, one is the absorption spectra, the another is the emission spectra. The absorption spectra is we are getting that once you shine light of some sort, like a UV visible, microwave, or anything, any electromagnetic spectrum, what we'll see is that a particular substance on which we want to record the spectra, the substance or the molecules inside it, or the constituent atoms inside it, they will absorb the spectra. Okay, they will absorb some of the light because of the quantization. Now that is the important, we are seeing spectra because of the quantization. If there is quantization, we will not see any peak, or will not see any broad peak or a spectral line. It occurs because there is quantization at the quantum level. Okay, now because of that quantization, it absorbs the energy. Once a particular molecule or a particular substance absorbs the energy, the other energy that it has not absorbed is given out. Okay, so for example, we give a broad spectrum, UV visible spectrum, for example, and once we give that UV visible spectrum, what will happen is that I'll show briefly here. So for example, we have light of some sort. Okay, so we give, for example, UV visible from 200 nanometer to 800 nanometer. Okay, so for example, we give this light to a particular substrate that is present inside our cuvette or anything. Okay, so one of the light, it will get absorbed in this by the molecules. Okay, for that the molecule can undergo various transitions. Okay, now and the rest will be given out. Okay, so that rest energy, as a result of, we'll see a spectrum correspond to that. For example, I will show you. 1 minute. And Okay, so first here we are talking about uh, today we'll be talking about spectroscopy. Okay, spectroscopy is a very analytical or useful tool for chemists or any sort of the scientists to find the nature of the different processes that are happening at an atomic or a molecular level, okay, or a crystal level, you might say. So today we'll be talking about spectroscopy. Now what I'm talking about is the spectroscopy is majority, we find it that it's of two types. Okay, we have an absorption spectroscopy and we have an emission spectroscopy. Now, in case of an absorption spectroscopy, what we actually do is we will give a light. Okay, so once a light is given, okay, for example, it has an energy that is equivalent to that of an h nu. Okay, and we have a cuvette of some sort. Okay, which contains our molecule of interest. Okay, then okay, I'm talking about the absorption spectroscopy. So what we give is, in case of an absorption spectroscopy, we will give a range of energy to that of our molecule of the interest that's present here. Okay, so if we, for example, we give a range of energy, if we plot energy as a function of lambda. Okay, so this is the intensity. Okay, so we'll give intensity, or in other words, we can write it as an amplitude. Okay, so we give intensity of the light. Okay, so once we give intensity of the light, for example, UV visible spectroscopy will give from 200 to 800 nanometers. Okay, then what will happen is this will be our the spectra that is given. Okay, then what will happen is some of the energy is absorbed by this. For example, this absorbed around 300 nanometers, it absorbs. So once we get a spectra, what we will have is we will have something called as an absorption spectroscopy. In absorption spectroscopy we will have, there will be a, so this is 300 nanometers. Okay, so that means what has happened is this 300 nanometers light, it is actually absorbed by the substrate, and this spectra is called as an absorption spectroscopy. Okay, in case of an emission spectroscopy, what we give is we give a light. For example, we will give a UV light, okay, to our substrate that is present here. Okay, so once we give it a UV light, this some of the amount will be absorbed, but this is our first step. The second step is we have to remove the light. Okay, so once we remove the light, we'll see what is the what is the intensity that is given by the particular substrate. So here we are looking for an this is an absorption spectra, and this is an emission spectra. Okay, so there are other types of the spectras. Actually, those are not spectras. You might have seen a concept called as an X-ray diffraction pattern. These uh, in case of an X-ray diffraction, we are actually looking for scattering. Scattering of light. Okay, not the absorption or the reflection. For example, if you give some light to a particular object, for example, we consider the diffraction. Okay, then what will happen is this object, it will reflect it all over. Okay, so this process is called as a scattering. So in scattering, in X-ray diffraction, we are basically looking for diffraction patterns. Okay, diffraction of the light by lattice planes. Okay, so similar case happens in case of a Raman spectroscopy. In case of a Raman spectroscopy, we are actually looking for scattered light. Okay, so this is the main concept regarding this. This is now once now this is our main concept. Okay, so this is how different types of the spectra are there. Now as I showed you before that there are different kinds of the spectroscopy, and this spectrum arises for because of the quantization of the levels inside a molecule or an atom. For example, if we consider a simple hydrogen atom or a simple hydrogen like atom, and we see that even both the Bohr's model of an atom or the Schrodinger's equation, if we solve for an hydrogen atom, we'll find the solution for different energy levels. That means the equation that will tell us uh, the energy of different levels. Okay, so in Schrodinger's equation, what we solve is h of phi to e of phi. Okay, so once we solve this equation, what we'll get is we'll get something called as, and we'll see how the energy depends on different parameters, and solving these equations we'll get a energy level. We will get an equation to calculate different energies, or in other words, in quantum mechanics we say that we'll get equations where the eigenvalue equations are satisfied. Okay, so this is an eigenvalue equation. Okay, so for example, the eigenvalue equation where are satisfied is En, that means the energy of different levels is equivalent to minus 13.6 is z square. Z is the atomic number divided by n square, electron volt. Okay, okay, so this is in electron volt is this equation. So what we find is that if for example n can range from 0 to n can sorry n can range, n cannot range from 0. Okay, so there will be this is a principal quantum number. Okay, n is a principal quantum number, and it can range from 1 to the above, and z is the nuclear charge. So if we see that different if we change the value of an n, okay, what we will see is, for example, we put n is equal to 1, that is shown here, for example, and for an hydrogen atom we'll see where are the energy levels, and z is equivalent to 1 for an hydrogen atom. So how much value we'll get minus 13.6. that means the first level is at minus 13.6. The negative sign indicates that you have to give energy in order to take an electron out. Okay, the process, so this is called as an ionization. Okay, so if we see, you might have heard about a theorem called as a Koopman's theorem. The Koopman's theorem states that the energy of a particular orbital is equivalent to negative of its ionization energy. Okay, so if you are ejecting an electron from any substrate or from an atom, that electron, while from the level it is ejected, the amount of energy that you have given to that system or to that atom to eject that electron is its ionization energy. Okay, so for example, for an hydrogen atom at one level, that means principal quantum number is equivalent to 1, will get energy of 13.6 electron volt. Okay, then what we'll do is we'll put n is equal to 2, we'll get 13.6 divided by 4, then 13.6 divided by 9, then 13.6 divided by 14. So what will happen is that means the for an hydrogen atom, in the middle there is a nucleus, there is an energy level whose energy is minus 13.6, then you have minus 13.6 divided by 4, around 5.6 or something. There is a quantization. That quantization, there is an energy level here, there is nothing in between, and there is an energy level here. Okay, now this is for a simple hydrogen atom. If you consider another another atoms, now this is a hydrogen atom. Okay, so for a hydrogen atom, the energy of the orbital depends only upon the principal quantum number n. But if we see that if you increase, you add more and more electrons, okay, to hydrogen atom, and to do so we'll get different atoms like helium, neon, argon. For them there is a factor called as electron screening. So one electron screens another electron from that of nuclear charge. As a result, the energy does not only depends on the principal quantum number, but also it depends upon the asymmetrical quantum number L. Okay, so here for a simple hydrogen it depends. So what we can see here is that different energy levels are quantized. We have one level, then there is nothing in between, then there is another level. Okay, so if you we take a spectrum for an hydrogen atom, very high resolution spectrum. High resolution means where we see good separation between different peaks. We'll see a very that structure called as a fine spectrum of hydrogen. So fine spectrum of a hydrogen tells us about the different molecular orbital uh, that are present inside the hydrogen. Okay, you will see that also in case of an hydrogen atom there is a little dependence on the orbital quantum number, and this is called as a lamp shift. Okay, that will not go there, but that for your curiosity you can read this lamp shift. But we'll see that if we take a spectrum for an hydrogen, we'll see different lines in the spectrum of hydrogen. Those lines actually will tell us the different separation between the different energy levels. Okay, so it is the quantization that is giving us the spectra. Okay, now if we go towards the helium atom, okay, for example if you go towards the helium atom, now what we have is helium atom is you have a two proton inside, then you have an one electron up and one electron down. So this circle that I am making, it's actually a vague representation of molecular orbitals. This is actually the molecular orbitals are not deterministic, so everything that happens at the quantum mechanics is probabilistic. So you have a sort of finite probability of an electron to be present here. Okay, so as I have written here, for helium atom we have a pair of electrons. Okay, and then correspond those pair of the electrons, we have the helium energy levels. And now since we have the two electrons that are present in case of an helium, then the energy of the helium atom depends upon the, as I have told you, it depends upon the orbital quantum number as well, not only the principal quantum number but orbital quantum number of the electron. Now why it depends on it, this is, for example, if you see that this is the electron probable density, okay, of different atomic orbitals as are calculated using the quantum mechanical equations for different molecular orbitals. Okay, you see that this 1s orbital, it has a finite probability very close to the nucleus. Okay, then you have an 2p. 2p is like this. If you plot 3D, it will be like this. Okay, so as electrons, they are more closer to the nucleus. As a result, once the electrons are more close to the nucleus, if there are other electrons that are here, these electrons are shielded from the nuclear charge. As a result, they will feel less nuclear charge as compared to that is actual present. So that is called as an effective nuclear charge. Okay, effective nuclear charge is the real nuclear charge minus the screening constant. Okay, now S and P orbitals, we say that they are more close to the nucleus. As a result, they have more screening power. Okay, they screen more electrons of others as compared to. As a result, what will happen is that the electrons that are present in other orbitals like D, F, okay, they will be less electrical charge, so they will not be exactly present as is given by their principal quantum number only. So for them, the energy depends not only on the principal quantum number but on the orbital quantum number. Okay, the orbital, that is the reason we plot the upwards principle. You might have shown the energy diagram. So in there you will see that 4f has less electron as 4 less energy as compared to that of the 4d. Otherwise it should be other way around. Okay, sorry, 5f has less as compared to that of the 4d. So This is how it works. Okay, so this is what I have written here. This can be attributed to the fact that the 2s electron penetrates more inside the charge of an 1s electron. The 2s is therefore less shielded from the attractive force of the nucleus than the 2p is lower in the. This dependence upon the orbital quantum number of a single excited state electron is accounted for the penetration of wave function and can be seen clearly in the energy level alkali metals such as lithium and the sodium. Okay, so that I have told you that what actually happens when we have more than one electrons. Okay, the orbitals come into the picture. Okay, you have to always remember that s and p orbitals have always lower energy as compared to that of an d and f orbitals of the same principal quantum number. Okay, why? Because s and p orbitals are more penetrated towards the nucleus, they are less shielded, while the other orbitals are shielded. Okay, so here actually I have shown you how it depends. Okay, so for example we will take helium atom. Okay, now if we have helium atom and we see that we have helium atom, it has uh, two electrons in its 1s level. Okay, now if it has two electrons in its 1s atom and then there is another orbital here, that is 2p. Okay, so one of the electron will go from here to the here, so it is first excited state will be 1 this. Okay, now this is 2s and this is 1s and this is 2s. Sorry, this is 2s, this is 1s and this is 2s. So after 1s you will have 2s, then you have 2p, 1s 2s 2p. So what will happen is that now at the ground state both electrons were present in 1s and they were paired, so that is the lowest energy state. Okay, now what we do is we go to the we give some light. Okay, it goes to the one of the electron, it goes to the another state. Now this there is a possibility that electron in the 2s can be both up spin or it can be down spin. Okay, because of that you will have two types of the heliums. You might have heard about the parahelium or orthohelium. Okay, so if the spin multiplicity that is given by 2s plus 1 is 1, that means the helium is singlet, it is called as a parahelium. If it is 2, then it is called as an orthohelium. Okay, so we have two states, parahelium and metahelium, uh, orthohelium, parahelium and orthohelium. Now you see, once we okay, so you see that once in these both parahelium as well as orthohelium, the energy levels are different. You see, this I have plotted, this is the hydrogen levels, this is the first level, this is the n is equal to 2, n is equal to 3, n is equal to 4. Okay, but if you take parahelium, this is s equivalent to 1, that means the ground state. Okay, then you have a 2s, then you have a 2p. If we compare that orthohelium, the 2s level is nearer to that of the 1s level. Why? Because of the spin multiplicity. Now higher the spin, higher will be the stability. Okay, so that means this state has is more stable as compared to that of this stable, and similarly it affects the other energy levels as well. Okay, so that is what I have written, is that another effect on the helium energy levels, it can be associated with the spin quantum number and arises from the spin requirement of the Pauli's exclusion principle. Note that for a given values of principal and orbital quantum number, the states with parallel spin are significantly lower than those with antiparallel spin. This is sometimes referred as spin effect and are summarized in Honda's rules. Okay, so that's what I told you, that if we have two orbitals and two electrons, they are more stable if they are parallel to each other because of spin correlation functions. Okay, so that is what is actually, that means in case of an atom, not only the uh, principal quantum number factors, but orbital quantum number, as well as sometimes the spin quantum number affects the energy levels. Okay, that you have to see. Okay, so this is I have already showed. Now there is an another effect that is called as an orbital orbit. The first one that I have shown here you people is supin. This is called as a supin effect. Okay, now there is orbit effect. In orbit effect, what happens is that, as I have shown here, for light atoms with multiple electrons outside the closed shell, we can combine the orbital angular momentums to give the resultant angular momentum L. Consider a vector model. We expect that we can get different values of L for a given set of individual orbital angular momentum. It turns out that the largest possible L values has the lowest energy. This phenomena is sometimes referred to as orbital effect. Okay, so how it see for different for higher atoms. Okay, what will happen is that if we have uh, you know that every orbital is we see it has two momentum associated with it. One is called as an orbital angular momentum, second is called as a supinangular momentum. Supinangular momentum will be when there will be an electron associated with it. Okay, now if you have an atom, okay, and it has electrons in two states, like two orbitals. Okay, so that means what will happen is that, or it has electrons that are in the same state, but it is an open shell. Okay, so it is not like a noble gas configuration. For noble gases, both total orbital and this angular momentum comes out to be zero in the ground state. Now what will happen is each electron has both its supin orbital angular momentum as well as the supin angular momentum as well as the orbit angular momentum. Now this angular momentum, it will give rise to the magnetic moment. Now magnetic moment is a vector quantity, or momentum is a vector quantity. So in order to get a resultant momentum, what we have to do is we have to do the vector summation. Okay, so for example, one has an angular moment of 1 L1, 1 electron. Second has an angular moment of L2. So what we will do is we have to since now what we can do is we'll write L1 plus L2, but another possibility is L1 minus L2 and all other possibilities that are in between. Okay, so this we is summarized as, this is called as a Gordon series. Okay, so where you do an from L1 plus L2 to L1 minus L2, all the magnetic moments are possible. Now out of those configurations, the magnetic moment that's called as L, which is highest, is more stable. So this effect is called an orbit effect. Here one orbital angular momentum affects the energy of the total levels. Okay, so that is what I have written for lighter atoms with multiple electrons outside the closed shell. Okay, so closed shell means where you have a noble gas electronic configuration. Okay, so once you have a noble gas electronic configuration, what will happen is that we have, and then after that you have different orbitals, and those orbitals, they have different electrons. Now those electrons will have both spin as well as the orbital angular moment. Okay, now we can add both spin and we can add the orbital angular momentum. Now let's leave the spin first. First we have to add what is the total orbital angular momentum. So we have to add the orbital angular momentum for both electrons, for example. Now that will be given from L1 plus L2 to L1 minus L2. So we have to do the vector summation. This is called as golden Glebich series. I don't remember, it's like Glebich series or something. Then that means you have a different angular momentum for different configurations. Now that angular momentum which has the highest possible value of an L, that means orbital angular moment constant, is called is the most stable. Okay, so this L is called as a total orbital angular momentum quantum number. Okay, so this is called as a Hund's multiplicity rule. Okay, so that's what I am saying. So this also affects. Okay, for example, I will tell you that this what I have told you previously is this is also summarized here. For example, so what is summarized here is what we have is we have 4p 4d configuration. Okay, so one is we have 4p 4d configuration. uh, Now first we'll take supin. Now this 4d1 4p1, so we have two electrons. Now two electrons have a spin of 1 by 2. That means both electrons can be up or both electrons can be up, one electron can be up or one electron can be down. So if it is up, total spin angular momentum quantum number will be 1. Okay, that will be 1. Similarly in this configuration it will be total angular spin angular momentum quantum number will be 0. Okay, you can we can so this is called as total spin angular momentum quantum number. From momentum quantum number you can determine the magnetic moment by just L into L plus 1 h by 2 pi, right? Or in case of an spin you can determine s into s plus 1 h by 2 pi, that you might have heard. Okay, this is called as magnetic moment. Okay, so each of this angular momentum has the information about the magnetic moment that occurs because of that configuration. Now this is called as, now what we have done is we had a one configuration. Now that configuration there is two possibility. One possibility is splitting will be that means total spin is 1 and total spin is 0. Now I told you before that the most stable one will be which has maximum spin, that means maximum spin, so this will be the most stable one. Okay, now we have another thing. What another we have is orbital angular moment. Now in case of an orbital angular moment we see that for L orbital angular moment. Okay, for S orbital is 0, for P is 1, for D is 2, for F is 3, right? That we know. Okay, now inside that L we will have different mz. Okay, orbit angular, there is another called as an ml or mz. Similarly we call it as an ml. It has different components. This has only one. This will have 2 multiplied by 1. This will have 2. Okay, so it is from sorry, this will have 3. It will have 1. So oh, yes, so we have p has in 3 different ml. So it is like for example if we take it will be better to show here. So if we consider a d orbital, okay, as I have shown that for an s orbital the orbital angular momentum L is given by 0. For a p orbital it is given by 1. For D it is given by 2. For F it is given by 3. Now corresponding to different L we will have different ML. Okay, this gives the orientation of the magnetic moment across with respect to z axis. Okay, for ML is always equivalent to 2L plus 1. Okay, so it tells us different orientations. For S there is only one orientation, that is 0. For P there are 3 orientations, -1, 0 and +1. For D similarly there are 3 different orientations. It will be +2, +1, 0, -1, -2. Okay, similarly for 3 there will be 7 orientations. Now if I will represent the orbital angular moment with as vectors, so how I can represent them is, for example, this is my z axis. Okay, this is my negative z axis. If there is this corresponds to my 0 ml. Okay, then we have a positive, then we have a negative. So if we have a positive, what we will have is we will have +1, we have -1. You might have seen about the conical representation. Okay, so for a conical representation what we do is we say that the orientation is somewhere on the surface of this cone. Similarly for this, the orientation is on the surface of this cone, because we are only able to measure the one of the component of orbital angular moment and the total orbital angular momentum quantum. We cannot measure all the three. So these are given by the complementary principle. Okay, so commutators and everything, you might have heard about them. Okay, similarly this is p orbital. If I will make d orbital, now d orbital is little. Okay, now for d orbital we have 6 orientations. Okay, first orientation I'll make is this. Okay, so this is when the value is d lm for this is 0. Then we'll make another value with probably red. Okay, that is, okay, for them the value is, sorry, it is +1, this is -1. Okay, and this I am telling you, this is along the z axis. Okay, then we will have another one. Okay, this is +2 -2. So you will have a different orientations corresponding to them. We say that we have dx d. For example, here we have represented that for this it is dz. Okay, similarly then we have dx, we have dy. Okay, so we give it a different orbital names. It actually depends upon this. Okay, so corresponding to them we can make them. Okay, so this is how. Since we know the one of the component and we know the total angular momentum, so we can show that the orbital moment is somewhere along this surface of the cone. Okay, so this is the concept regarding the orbital angular momentum. Okay, now what I have shown here is yes, here. So what I have shown here is we have the supine angular momentum quantum number, and there is a supine multiplicity. Okay, there is supine multiplicity. Now probably I will show you here. Okay, so we will call it as so this is called as an orbital coupling. Okay, so the configuration that we have is p1 d2. Okay, so we have p1 d1. Okay, this is our configuration. Okay, now we have already known that how much will be the l1, sorry, small l, that means the orbital angular moves. Okay, so first we'll write how much will be the s1 small s and how much will be the s2. S2 is the supine magnetic moment. For s1 it is 1/2, for s2 it is also 1/2. Okay, now we again do how much will be the total s. The total s will be equivalent to, as I told you, vector summation from s minus s1 minus s2 to s1 plus s2. So s will have 2, 0 and 1. Okay, if we represent this 0 it will be, and if we represent this 1 it will be this. If we represent in terms of orbital uh, since we have P and D, this is P, this is D, so the P will be, for this it will be, electrons will be like this, and for this configuration, sorry, this is, okay, so it will be this. So this is our on the basis of a spin multiplicity. Now what will depend, will represent orbital multiples. For orbital multiplicity, for orbital, what will write is how much is the uh, orbital uh, quantum number for one electron, how much is the orbital momentum for another electron. For orbital angular present in the P, we have how much, sp1. For in the 2 we have, in the L we have 2, so we have orbital quantum number for one electron 1, for another electron 2. Now how much will be our total L, total orbital angular momentum quantum number? It will be from L1 plus L2 to L1 minus L2. Okay, so L1 plus L2 is 1 plus 2, okay, to 1, it doesn't matter. Okay, so this is 3 to 1. This has to be positive. Okay, so we have 3 2 1, that means 3 configurations are possible, which has L is equal to 1, L2 and L3. Now corresponding to each of these L, we represent them as Millikan term symbols. Each of these L will correspond to different configuration. So each configuration, in order to represent different electronic configuration, we represent them in the form called as a Millikan term symbols. For Millikan term symbols, what we'll have is, we'll take the base L corresponding to 1, it will be P, capital P. Corresponding to 2, it will be D, capital D. Corresponding, it will be F. So we have 3 configurations. Okay, 3, S, P, D and F. Okay, 3 configurations we have. Now when we have the 3 configurations, okay, so that is what we are showing here. We have an F, we have an D and we have P. So 3 configurations. Now according to the Honda's rules, which will be more stable, that F will be more stable. Also I have told that each of these configurations will be having both singlet as well as triplet, singlet as well as triplet, singlet as well as triplet. This is because of supin multiplicity. Okay, so triplet will be more stable as compared to singlet, as compared to doublet. Then what we have to represent is, we have to represent the total angular momentum quantum number. Okay, so total angular momentum quantum number is, we have to do the same way, uh, one angular momentum plus another angular momentum. Okay, so for example, if we will take F3, okay, L is here 3, how much is S? S is 1. Okay, this is super multiplicity. Then total J will be from L plus S to L minus S. Okay, so J will be from L is 3 plus 1 to 3 minus 1. J will be given by 3 plus 1 is 4, 3 2. So in J we will have 4 3 2. So this setup is called as a supin orbital interaction. Okay, supin orbital interaction. first what we did is we did the orbital interaction, spin interaction, then orbital interaction. So we calculated the total spin quantum number, then total angular quantum number. Now we are getting the total quantum number. Okay, total magnetic momentum quantum number. Okay, this is called as a spin orbital interaction. Now this thing is called as a spin interaction. This thing is called as an orbital interaction. Okay, so this type of a coupling is called as an LS coupling. So first we did the total L, then total S, then called as an okay. So there are two main that you should know. The thing that we have followed is called as an LS coupling. Okay, so in LS coupling what we have done is we have calculated first L, then we have calculated S, then we added them together to get J. Okay, there is another type of a coupling you might have heard, that is called as a JJ coupling. Okay, so in JJ coupling what we have is we calculate the small s plus small l. Okay, then small l plus small l, that means each electron we calculate the orbital angular momentum quantum number, and then there is an interaction between orbital and spin, and then we calculate the small j, that means j1 plus j2, then we calculate G. So this is possible. This is true in case of very higher atomic orbitals, higher atomic number molecules, whereas LS coupling holds true for smaller atomic number of it. Now what we have shown here is we have got J43, that means J3 has 4 states. J3 has 4 states, 4 3 2. Okay, similarly, okay, it has 4 states. Similarly, that means which one will be the so J has 4 states. Now we'll consider the second case, D3. Here total L is SPD 2 and S is 1, so J will be equivalent to L plus S to L minus S. That means J is equivalent to 2 plus 1 to 2 minus 1, that means 3 2 1. Thus D has 3 configurations, 3 2 1. Okay, so it has this configuration, it has 3 states. Okay, then last one we have is P3. Here L is 1 and S is 1, so J will be equivalent to L plus S to L minus S. J will be from 2 1 0. Okay, so P has 3 states. What states there will be? 2 1 0. Okay, so that means what we have done till now is, if we have a configuration P1 D1, okay, this P1 D1, it first what it will do is it get a split on the basis of now we have calculated the total status for SP and D. Okay, we will calculate now for F1 D1 and P1. Okay, now we have F1. Okay, so for F1 what will be the L? S P D F 1 2 3, it will be 3. S here is 0, so J is equivalent to 3 plus 0 to 3 minus 0. That means only one state is possible, so F1 3. Okay, then we have P1 L2 S0. That means here also only one state possible. Then we have, sorry, this is D state. Then we have P state. P1, you will see that we have only one state. P state. Okay, so we have calculated what are the all states that are possible by a single electronic so single electronic configuration can have multiple states. Okay, now using the Hund's rules of maximum multiplicity, what we can do is we can arrange them on the basis of their energy. Okay, so for that what we will do is, we will write whatever configuration we have. We have P1 D1. Now this is configuration. Okay, the first step that will happen is, okay, first there will be supin interaction. Because of the supin interaction, you will have either a triplet where S is equivalent to 1, or you will have either a singlet where S is equivalent to 0. Okay, then this is more stable. Okay, then we'll have supin orbital. Now doing the supin orbital interaction, this has how many states? 3 states. Okay, probably I can change the screen color. Okay, now what we have is, we have now each of these will give 3 states: 1 state, 2 state, 3 state. Similarly this will give 3 states: 1 2 3 state. Okay, now the lowest energy state will be F D P. F D P. You must remember that all of these will have supin multiplicity of 1 1 1 3 3 3. Okay, this gives only one state. That means P1, this gives one state, this gives one state. This is 3 2 1. Okay, now this P, if we'll use some this color, okay, okay, this gives some more states. This gives 3 states. Similarly this gives 3 states, and this gives 3 states. Okay, so F3 states are F triplet. Then we can see them here: 4 3 2 4, then F triplet 3, then F triplet 2. Similarly we have D D D, triplet triplet. So the highest will be 3, then it will be 2. What I can do is to make it little more visible. Okay, so these three states we have now. One is P3, it will get split into 3 states. Okay, then we have D3 split into 3 states. Then we have F3, it will get split into 3 states. Okay, the F3 states will be F3, I think 4, F3 3, F3 2. D will be 3 states, 3 2 1. P will be 3 states, 2 1 0, 2 1 0. Okay, this is the increasing energy as we have shown here. Now, so that means a single electronic configuration, if we see, it can have different states. Now depending upon where the electron is, we can have different states. Okay, we can have, okay, so different. Now depending upon their total orbital angular momentum quantum number, or total spin quantum number, or total angular momentum quantum number, we can know which energy is lowest, which energy is highest. So same we have shown here. We have a spin coupling, orbital coupling, and then spin orbital coupling. So I will read here what it is written is: with multiple electrons there is an additional source of splitting of energy levels, which is characterized in terms of another quantum number called as a total angular momentum quantum number. Okay, the source of splitting is called as spin orbital effect. When the for lighter atoms, the spin and the orbital angular momentum of individual electrons are found to interact with each other strongly enough that you can combine them to form the resultant spin and the resultant orbital angular momentum quantum number. This is called as a Russell-Sanders coupling, or LS coupling, that I have shown here. That there are I have told you previously that there are two types of the couplings. Okay, one is Russell-Sanders coupling, and second is called as a JJ. So what we have done is Russell-Sanders coupling. That is only true for lower atomic numbers, but higher atomic numbers you have a JJ coupling. Okay, the SN are combined to produce the total angular quantum number. This is called as. Now with the external, now we have created different states. Okay, so that means even if you have an electron with, you have an atom with 2 electrons only. Okay, so you will not expect that you will get a single line, but it has different states corresponding to different energy levels. Now if we give an external energy, the electron can split between, the configuration can change, it can give a different energy state. For example, the F32, it will go to D31. Now all the transitions are not possible. We have to see the rules which states that which of the transitions are possible, which of the transitions are forbidden transitions. So they are called as, if the transitions are allowed, they will happen; if the transitions are forbidden, they will not happen. They will happen, but to a very weaker extent. Now there are other effects which can lead to relaxation of the selection rules. Now here what we are showing is that even for a atom with only 2 states, with only 2 electrons, we can have different states. Now once we give the energy, what will happen is the electrons can reconfigure from one configuration to another configuration. As a result, we will see some line corresponding to that, as I have told you before. Okay, now when an external interaction such as a magnetic field is applied, then further splitting of an energy levels occur. That splitting is characterized by, okay, so we have shown here. Now what we'll do is we'll put this thing into an external magnetic field. Okay, and this external magnetic field now interact with the internal magnetic field, because magnetic field is occurring because of the spin angular momentum or orbital angular momentum. Now one is the two magnets interact, they can either align in the same way or they can align in the opposite way. If they are in the same direction, this will have higher energy. If they are in the opposite direction, they are, this is like a two magnets. If we take south has to be go to the north and north has to go to the south, then it's a stable configuration. But however, if we put opposite, the configuration is unstable. Similarly here the configuration is highly energetic. So what we have done is we have done additional splitting because of putting our particular atom inside the magnetic field. This effect is called as a Stark effect. Okay, sorry, this is called as a Zeeman's effect. So if we put in terms of a angle, in terms of in a magnetic field, it will cause a splitting. It's called a Zeeman effect. Similar effect is happening if we put in an electrical field. Okay, this is called as a Stark effect. So you have a Zeeman effect that occurs because of application of external magnetic field. We have a Stark effect because which happens because of interaction with the external electrical field. So now what will happen, that means we have created an additional effect. Everything occurs because electrons has magnetic moment. Okay, spin and the orbital magnetic moment. Okay, so now yeah, this is what I have actually shown before, that first we have a configuration of 4p1 4d1. Then first there will be spin interaction. Okay, when there is a spin interaction, then what will happen is you will create two states. Okay, so once the two states are created, we can have singlet state and triplet state. Singlet state is according to Hunter's rules of multiple velocity more stable, so it will go down. Then singlet state will have different orbital interactions. Then orbital interaction with which gives the maximum orbital interaction, it will give maximum more stable. Okay, this is called as an F. Then we have a D, then you have a P, then similarly you have an F. Then what we have is we will put spin orbital interaction, so then we will have more states. So here what I have done is it is 2 3 4. So the total angular momentum should be lowest, will be more stable as compared to that of a here. In my this we have probably put the opposite direction. Okay, so we can write this is increasing energy. Similarly this is energy increase. Now when we do the, you have to remember that once we do the this LS coupling, or we do the Gorton-Gilbert series, all the configurations might not be possible. Okay, so all the configurations might not be possible. For example, if we have a D2 configuration. Okay, for example, so you have to take care of that. Once we you make different electronic states that are possible from electronic configuration, you have to take, for example, in case of a D2 configuration, now both electrons are present in case of E. If we take that L, now first we have to take S. So we have an S1 is equivalent to 1 by 2, then S2 equivalent to 1 by 2. Okay, then the total S will be either 1 or it will be 0. Then we'll say that spin multiplicity will be 3 or 1. It will be this state is called as a triplet, this is called as a singlet. So we all know that triplet state is more stable than the singlet. Now you have to see, now here in the previous, since two electrons are present in two different orbitals, there was no issue. Okay, but now we will have an issue of a spin pairing. Okay, so what I'm telling you, this is if, for example, in this state, first I should have told you that how to put in different energy orbitals. Okay, briefly I will show you what are the different electronic configuration. Okay, probably I will show here different electronic configurations possible corresponding different electronic states. Okay, so these symbols, they represent different electronic states, you have to remember that. Okay, now this is possible. Now if we take L, okay, L1 is SPD, 2, L2 is also 2, so we can say that L, total L will be L1 plus L2 to L1 minus L2, right? That means L will be from 4, 3, 2, 1, 0. Okay, but if you see that for this state we taken this is a d orbital. Okay, you see, I will try to plot. This is our d orbital. 1 2 3, 1 2 3 4, 1 2 3 4 5. Okay, for d orbital the okay, we can write as m l. Okay, this is 0, this is minus 1 minus 2 plus 1 plus 2. Okay, so in order to make L4, now in order to take L4 we have to put, and also in order to take L4 and also spin multiplicity should be 3, we have to take both or both in this configuration, then only total momentum will be 4, but that is not possible because uh, two electrons cannot have the same number of 4 quantum numbers, so this configuration is not possible. As a result, this 4 is not possible. Okay, then we'll make the 3. So we are making only triplet states. 3, 1 will be present here, another will be present here. 2 plus 1 is 3, that is possible. Okay, L3, L4, S, we are always keeping 1. Oh, sorry, I'll write super multiplicity. Okay, then S3, L2, we can have different for this, like this, for example. Okay, so 1 2 3. Similarly you can make all other states, putting then another one in this, another one in this, or another configuration. These states are possible, but this state is not possible. Okay, so as a result this configuration, so you have to always take care of how to make the electronic states, but you have to take care of the quantum numbers, if it is allowed or not. Okay, so this is what I was saying. So now here it is shown that f is equal to 2 3 4, it has 3 states, this has 3 states, these are 1 states. Okay, you have to always remember while like Hunter's rules of maximum multiplicity, which electronic state has lowest energy. First we have to consider the spin multiplicity. That state which has highest to spin multiplicity is the lowest in energy. That is the reason 3 is always the lowest energy. Then we had to consider L, total orbital. That configuration which has highest orbital angular momentum has the lowest energy. So F has D and P. Then there is spin orbital interaction. Those orbital which has, it is J. Okay, so they J, which is lowest, has highest. And now there are certain also rules that if the electronic configuration is more than half filled, then it is actually the opposite. Okay, so that I will not give there. So what I have told you is that how the different energy status are possible in an atomic configuration. Okay. So till now what I have showed you is that how different atomic states are possible in a single electronic configuration, and how we can see that what are the different configurations that arise because of a particular electronic configuration. Now those status, they can arise by internal or an external effects. Internal effect includes the spin coupling, spin orbital coupling, and the orbital orbital coupling. And the external factors include the magnetic effect, then it's called as a Zeeman's effect, or electrical field called as the Stark effect. Now we have seen that any atomic, any orbital, it has different, any system or atom, similarly a molecule I will show you, it has different electronic states. Now a transition can happen between two electronic states. It requires a particular amount of energy. Okay, so Bohr's principle, once we give an energy that is equivalent to that of the states between, we'll see a peak. Okay, that means we'll see an absorption has happened in that place. Now if we are measuring how much energy is absorbed, it's called as an absorption spectra. If we are measuring that electron will come from this state to this state, we'll see an emission spectra, because we are measuring emission. Okay, so here is like a brief introduction that how spin orbital and spin interactions work, and what is the different spin orbital. So I will just read it because I have already explained it. Okay, so for example here what we have shown is that there is an interaction between two different spins. Okay, so the total spin antisymmetric will be multiplication of the two spins. Okay, so it is like if we have a two electrons, if we have two system, and you know the wave function of each system, then the total wave function will be multiplication of these two wave functions. Okay, so psi 1 plus psi 2, but actually if we want to include the Pauli's exclusion principle, then what you have to do is you have to take a linear combination of these two, or you just make a Slater type orbiter. Okay, yeah, Slater determinant. Okay, that you will read in the quantum mechanics. So I will read here the effect of the spin interaction is noted in Hunter's rule. So Hunter's rule first tells us about the spin interaction. When the two spins interact, that configuration which has the highest spin multiplicity has the lowest energy. If you have two electrons, then the state in which these spins are parallel, that means S1 is called as a triplet, will be lower in energy than the state in which their spins are antiparallel, called as a singlet state. So triplet states are more stable than singlet state. Okay, higher the spin multiplicity, more stable. This is called as Hunter's rule 1. The result is correlated with the fact that now this is the why is it happening? It is because of an some effect called as an electronic correlations. Okay, so that is actually shown here. The result is correlated with the fact that two electrons are identical fermions. Okay, and the wave function which describes their part must be antisymmetric. Okay, with respect to exchange of electrons, it gives a Pauli's exclusion. The wave function can be construed to be a product of space and spin wave functions. Okay, uh, so this is a common factor, common strategy that we are using is that if you have a electron, and now we know that electron has both space as well as it has both spin, so we can separate the two total wave function into spin contribution, spin wave function, and the space. So we call another part is called as space orbital. So we have a space orbital and we have a spin orbital. Multiplication of two will give us a real orbital that we have. Okay, the fact that the spins are parallel make the spin part of a spin wave function symmetric and forces the space part to be antisymmetric. an antisymmetric space wave function for two of the electron implies a large average distance between them than the symmetric wave function of an anti-symmetric space wave function of the two electron implies a large average distance between them than the symmetric wave function of the same type. The probability is the square of the wave function and forms a simple functional point of view. The square of an antisymmetric wave function must go to zero at the origin. So in general, the probability for small separation of two electrons is smaller than for the symmetric wave function. If the electrons are on average further apart, there will be less shielding from the nucleus by the electrons, and the given electron will therefore be more exposed to the nucleus. This implies it is more tightly bound to information. So what this statement is for example, if we have, since we know that electrons are fermions, so fermions will have an should have an anti-symmetric wave function. That is a Pauli's exclusion principle. Okay, so they have an anti-symmetric wave function. Now if you have they have an anti-symmetric wave function, and since if the two electrons are parallel to each other, now if they are parallel to each other, that means space spin orbital is same. Now their space orbital must be different. So once their space orbital is different, what is the probability for this, that the combination of the two, it will be zero if both space wave functions are zero. Okay, so what actually it means is that if we have two electrons, electron 1, electron here, okay, now the total combination of these two, these are fermions, the total wave function psi t, it must be antisymmetric. Okay, since spin is same, that means the space orbital must be antisymmetric. Okay, now antisymmetric space orbital implies that if wave function of 1 and wave function of 2 at a particular point is always 0, because the probability will be psi 1 psi 2 minus psi 2 psi 1. This is an antisymmetric wave function. Okay, so this is antisymmetric wave function, total antisymmetric wave function. Now if we take the square of the, that will give us the probability. Okay, so square of this will be psi 1 psi 2. Okay, so this is the probability. Now if that means this is the probability. Now if both at a particular point psi 1 is equivalent to psi 2, so what will happen? I think I have done something wrong here. Okay, so this is not so what it actually means is that the spin an anti-symmetric wave function of two electrons implies a large average distance between them than the symmetric wave function of the same type. The probability is that the square of the wave functions, and from a simple functional point of view, the square of an antisymmetric wave function must be go to zero at the origin. So if you take the square of this, it must be zero at the origin. That means the probability that the two electrons is present at the same point in the space is zero for an antisymmetric wave function. So in general, the probability of small separation of electrons is smaller than the symmetric wave function. So if we have an antisymmetric space wave function, the probability that the two electrons will come closer is very less as compared to that for an symmetric wave function. Now if the probability has decreased just because we took an antisymmetric space wave function, that means two electrons will not come near to one another. As a result, when they don't come near to one another, electron uh, correlation, electron electron interaction, both are negative charge, they will increase the energy. So in other case, that means if you have an antisymmetric wave function, they will decrease the energy. This is called as a space correlation. Okay, if the electrons are on average further apart, then there will be less shielding of nucleus by the other electron. So the one electron is not, also another effect is there will be less shielding of one electron because of that electron. As a result, both electrons will be exposed to the nucleus and it will give lower energy. Okay, so it in one of the book by Atlas and Zebo, they write that once you have a antisymmetric wave function, an electron creates a Fermi hole around it, in which the other electron will not come. So once the other electron will not come, that means the electron electron interaction has decreased. Also, this electron and this electron is not nearby, they are far from each other, so this cannot shield this. As a result, both electrons are exposed more to the nucleus, which otherwise would not have been the case. When they are more exposed to the nucleus, the energy will decrease because of a positive negative interaction. So, and that is the reason, those systems which are having higher spin multiplicity are more stable because of the spin correlation, as compared to the system which are having same multiplicity. Okay. So now we have also second Hund's rule, that is spin orbital interaction. Okay, see, but first I will read what is actually written here. Okay, if the two electrons in an atom spend a lot of time close to each other, then they contribute a repulsive or a positive potential energy, implying that their energy levels will be higher. If the electrons are orbiting in the same direction, so have the large total angular momentum, they meet less often than when the orbital are in the opposite direction. Hence, their repulsive average is less. The fact that such electronic configuration has less energy means they will be filled first, and is called as the Hund's rule 2. So here we are trying to explain the Hund's rule 1 we have explained, right, because of spin correlation. Now we have the Hund's rule 2. In case of an Hund's rule 2, what happens is that we always say that which has a total angular momentum higher, it will it will be lower in the energy. Why? Because see, the electrons have an angular momentum. If you have two electrons, both electrons have angular momentum, it is only possible because the angular momentum, if you say if the electron moves like in this direction, angular momentum will be in the z direction, right? Similarly, the angular momentum, so if we have two electrons whose angular momentum is in the same direction, sorry, in the opposite direction, so that means one electron is moving rightward or another electron is moving leftward. That is the reason their angular momentum will be opposite to each other. Okay, when they are moving opposite, they will meet more often, because one is moving clockwise, another is moving anti-clockwise. Once they meet more often, this electron repulsion will occur. As a result, it will increase in energy. But if you move both electrons in the same direction, this way as well as this way, so they are relatively moving with each other. As a result, they will interact less often. So because of that, you will have lower energy. So this is the reason that why the states which have higher orbital angular momentum has lower in energy. We have first explained this Hund's rule 1. Now this is the Hund's rule 2. So those orbitals which have lower in the energy will have which have higher orbital angular momentum will have lower energy. Okay, so this is orbital interaction. Then we have also shown this is the singlet and triplet molecular states. If a pair of electrons occupy the ground state of the molecule, the electron spin state of two must be opposite. So we always know the Pauli's exclusion principle. If two electrons are present in the orbital, their spin must be opposite to each other. Okay, this states with that means there is no net spin angular momentum, and this is called as a singlet state. Okay, so this is called as a singlet state. But if one of the electron is present in another orbital, that means which is higher to its energy, and its spin can be both uh, downward, or its spin can be both upward. So there are two configurations possible. That is what is written. If one electron is elevated at high energy levels, the two electrons can be paired and unpaired with both electrons oriented in the same direction. The unpaired spin states are called as S and has three possible orientations with respect to an applied magnetic field. This is called as a triplet state. Now if you see that this singlet state, total spin angular momentum is 0, so it will not interact with external magnetic field, so no Zeeman effect. But if you see the excited state where the two spin states are in the same direction, this direction, okay, this state, if we put it in the external magnetic field, for example we apply a magnetic field alongside axis like this, now there can be two states happening. This can they can orient themselves towards the magnetic field, they can orient themselves against the magnetic field, or they can orient themselves like sort of this. So as a result we have three states. This is called as that's the reason it's called as a triplet state. So in Zeeman it will have three states possible orientation, it will have three states. Yes, okay, so that is the reason this has singular state, and this is called as a triplet states are always more stable as compared to the singlet states. Now till now we are till now we were talking about the properties of atoms, okay. Till now we were talking about the atomic properties, okay, the properties of atoms. Now atoms are very simple, okay. So you have a single atom, you have just electronic energy states, right? So that is very okay. I am here. Okay, so till now what we have seen is we were dealing with atoms. Now atoms have only the electronic energy levels, okay. Now if we go towards the molecules, the situation becomes more complex, okay. Now if we have two atoms make a molecule, these atoms can also vibrate, they can also rotate, okay. Also they have different molecular orbitals, so electronic states, okay. So they will have different types of molecular spectra. The more complex the structure, the more complex will be the spectra, okay. For atoms we'll have only electronic spin, electronic spectra, but for molecules because of the complex structure we'll have rotational states, we will have vibrational states, we'll also have transition states, but because the transition they are not quantized, so we won't see it. So that means we'll have different types of the spectra. Now different energy levels will have a different separation in between them, okay. So we have a electronic energy level, then we have another electronic energy level, the separation between them is for example this much. Then we have a rotational energy level, the separation will be vibrational, the separation will be lesser. Then we have a rotational, then the separation will be lesser, okay. As a result, if we want to see a molecular spectra we have to give different energy for excitation. So if we see the for example, if I will say that electronic energy levels, if we want to excite a molecule we have to give in UV and visible region, okay. Now if we go lower, we are in infrared region. In infrared region we can't excite a molecular we can excite a molecule from one electronic state to another electronic state, but what we have to do is we have to we can excite only between different vibrational and rotational states, because the energy is required for electronic states is higher than is given by the infrared. Then we go to the next, we go to the lower, like microwave. Okay, we will be able to excite only the rotational energy levels, not the vibrational. And then now, depending upon the structure of a molecule, we can deduce that where a particular molecule can have different rotational, vibrational, electronic transitions. Now this becomes a tool for chemists for structural elucidation. Okay, so spectroscopy is a tool in which the chemists can know a particular molecule or particular material without getting their hands dirty. Okay, so we are using radiations in order to elucidate different transitions and elucidate the structural properties or the electronic properties of materials. Okay, so that is what actually shown here. The atomic molecular spectra is like the same as I had told in atomic spectra. We had different levels. Similarly, we have molecular. Now molecular levels are more complex uh, than atomic levels, because of the rotational and the and vibrational states that are possible. So as I have shown here, the molecules have molecular structure, and from that structure it has a molecular spectra. Now if we know the moleculars, if we have the molecule, okay, we know, we can deduce its molecular structure, and from that molecular structure we can know what is its spectra. If we have the spectra, in turn we can deduce what is its possible molecular structure, and from that we'll know what is the molecule. So this is what chemists do. We have some molecule, we take molecular spectra, from that we can illustrate the structure. Now as I told you, the molecular states are complex as compared to the atomic states. Okay, for example, as I have shown you here, this is the, if we take for example a simple hydrogen atom. Okay, a diatomic molecule, from here to here, this is H1 and this is H2. Okay, and this is the increasing energy, this is their internuclear separation. Okay, if we take, this is the electronic state, this Morphy potential curve, and this is the electronic state. So this is the electronic state 1, that means the ground state. This is the excited state. Now each of these electronic states has small vibrational states. Okay, and then each of these vibrational states has small rotational states. So if we have to do a transition from an electronic state from here to here, that means in between the molecular orbit, we have to excite an electron from this molecular orbital to this molecular orbital. We have to use higher energy. Then if we have to excite a molecule from this state to this state, or this state to this state, that means uh, vibrational transition, we have to give a little less energy. Then if we have to do, then we have to give less rotational energy. Okay, so simple is the case. For example, I will simply show you. For example, if we have two hydrogen atoms. Okay, we have two hydrogen atoms like H and H. You might have heard, if we have two hydrogen atoms, we'll create two molecular orbitals. Okay, out of two atomic orbitals we can create two molecular orbitals. In one of the molecular orbital, we can so here, if we have two hydrogen atoms, okay, so we have this hydrogen atom, we have this hydrogen atom. Okay, now if this is psi A and psi B. Now psi A is equivalent to psi B, you have to always remember it. This is the atomic wave function for hydrogen 1, this is the atomic wave function for hydrogen 2. Now here we are using it for, but we will not be able to differentiate it. Okay, so we want to mix it, we want to create molecular orbital. So you have a molecular orbital 1 and you have a molecular orbital 2. There are two ways to combine them. One is psi A plus psi B, second is psi A minus psi B. So two states are there. If we take the nuclei of one, we take the nuclei of another. Okay, so this is the nuclei, and what we do is we plot the s orbital wave function. Okay, so how it will come, like, so s orbital wave function comes like this, right? Similarly here we'll have like this. Okay, so this is psi A, this is psi B. When the separation between them is very large, this is the D. But once they come closer to each other, we'll create two states. One state is, I'll make that state in green, in which you have one A here, you have B here. This is A, this is B, this is A, this is B. The electronic wave function will actually have, okay, so this orbital is psi m1. What these orbital have, as if you see in this direction, it has a finite electron density in between nuclei A and nuclei B. As a result, this finite electron attracts this nuclei and this nuclei. Okay, so because of this, this hydrogen is stable, and this is called as a bonding molecular orbital. In the opposite direction, what we can do is same separation, but there will be zero electron density in between this nuclei. This is called as antibonding molecular orbit or psi star. Okay, so what we have created is, if we represent this system, this one, so here we represent two orbitals as A, B. This is A, this is B. In this system, how we can represent, this is A, this is B. We can represent the electron density like this. Okay, but in this system, what we can represent is, this is positive phase and this is B is negative phase. Okay, so this, it is because of the bonding molecular orbital that the system is stable. Now we have created the two states. Okay, if we want to go a transition in between these states, we need some energy, but there is more complex. These are not only the states that can be arising. Since they are two hydrogens now bind to each other, we can consider them as balls, right? And these balls, they can vibrate. Okay, so they can go this way or they can go in the opposite direction. Because of that, you will have different vibrational states. Okay, but that is only not possible since this is these are like sort of a, these are not a sort of point or spheres. What they can do is they can rotate in different directions. As a result, we will have rotational states. Cool, so we have electronic, we have vibrational, rotational. Okay, now now we'll represent the uh, we'll represent an energy surface that is like this. Okay, and we'll represent the, it's not coming fine, but okay, this. Okay, so this is the first electronic energy state, this is the second electronic energy state. Okay, I'll represent the vibrational status by this, and rotational status by green. Okay, so this is energy, this is interatomic distance. So if we want to try, we want to see this why this electronic level has this shape. So you consider a we can consider two states like hydrogen A and hydrogen B. Okay, if they come very close to each other, so very close to each other they'll come, what will happen is that they will repel from each other because you are creating the nuclei very close to each other, so they will repel. As a result, the energy will increase. That is why this state is coming. Okay, now if they will go far from each other, so this is the two, this is the normal, this is A, this is B, and then this is A, this is B. Okay, so if this is 1, this is 2, this is 3, 1, they are very close, that means one state is here. Now if they are very almost sort of a intermediate distance, that means is the lowest, it is here. Now if they go very far from each other, okay, the interaction will decrease. As a result, they will become equivalent to that of their sort of equivalent to that of their normal individual hydrogen atoms. Okay, then the state will be here. So you have two states, 1, 2 and 3. Depending upon the intermolecular distance, you can have strong repulsion, strong attraction, or no attraction at all. Okay, so that is the reason these are plotted. Now this curve can be clearly plotted using the Morse potential curve, or 12 secant mu potential curve. Okay, so this can now I have told you that these states, these vibrational states, they are not equidistant. So once you go on increasing the number, that I'll tell you that there is called as an harmonicity in the vibrations. Okay, similarly the rotational states, they come closer to each other because when we go from higher to higher rotational status, it's because of the centrifugal distortion. Okay, so different distortions arise, as a result you will have, so this is sort of have made for a perfect system. Okay, now what we have is, I'll just finish this one, then we'll write. So as I have shown you that if we want to have electronic transition, we want to shift from here to here. If we want to have a vibrational transition, we want to shift from this level to this level. If we want to have rotational, we want to shift from this to this. Okay, so these, as you see, there is a different energy separation in between these levels, so you can have different types of the transition in different range of electromagnetic spectrum. Okay, the most commonly observed molecular spectra, they are involving electronic, vibrational, and the rotational transition. For a diatomic molecule, the electronic transitions can be represented by plots of potential energy as a function of internuclear distance. Now it is for a diatomic. If you have more complex system, the potential energy surface, we call it, it's more complex. Electronic transitions are vertical and almost vertical. Now I will plot, I'll tell you in this, these are called as a Frank-Condon principle, that the electronic transitions are always vertical because the electronic transition happens so fast that the nucleus doesn't have that time to relax. So first the electronic transition will happen, then the nucleus will relax. As a result, once we excite a molecule, the electronically the molecule remains in a thermally excited state called as a state, then it comes down through relaxation. Okay, vibrational transitions occur between different vibrations of same electronic state. Rotational transition occur most between rotational levels of same vibrational state, although there are many examples of combination vibration rotation levels of a light molecule. So I have told you about that. In today's lecture, we have seen why there is an atomic spectra, what are the different atomic spectra, how from a perfect two electron atom we can have different states. Then from those status we have the atomic spectra. Then I have briefly told you what are the different status or different transitions that are possible in case of a molecule. Now next lecture will go the forward. Okay, all these lectures and the information will be available on the YouTube and the drive, that is link that is provided by the NPTEL. Thank you so much for today's this. We'll meet next time.